This is a short video about using enterprise level databases. As I mentioned, other material, enterprise level databases are ones that are going to be installed as servers. In fact, this is Postgres, and if I go into Task Manager and I go to Services, you'll see that Postgres is installed in here somewhere. There it is. Okay, it took me a minute. PostgreSQL is officially the name, but most people call it Postgres because it's easier to pronounce. But this is actually a service, so it runs in the background. It's hidden inside your computer, like all these other services. Doesn't take up much computer cycles or memory until you start using it. But that's actually the database. So it runs out in the background as a service. Now, all of these databases are going to have software that will allow you to talk to the server in the background. The database itself, like here, you can see I've got my servers on this local host or this local computer, and then in there I've got a series of databases. This is one for EPSG codes, HSU, IDIS, the Integrated Taxonomic Information Database, one I'm working on for the history of the world, and some other stuff with projections, and then an old version of the Yurok fisheries database or Trinity River database we're working with the Yurok tribe. I've since moved it into SQL Server, which is another enterprise level database. MySQL is another one, Oracle is another one. Those are the main ones. There's a few others. But I continue to use Postgres. It's free, it's open source. You can download it onto your computer. And then you can't get PG admin anymore. It's now moved to a web interface, but I'm used to this one, so I'm going to use it. And again, this is a database inside of the server. You can have multiple databases. So this is one, we've got others. Databases are all going to be presented a little differently, but they're all going to have the same basic functionality. The core one that we really care about is tables. So here's a series of tables that I have, and if you open up any of these are ones I've created, there's going to be some way to view the data so that I can look at it. And here's a taxon table, or a table of taxonomic names, taxonomic identifications, typically known as scientific names. But the way IDIS is organized, it includes genus, species, family, phylum, all of those different taxonomic levels in the same data table. So that's why it's called taxons. I'm kind of used to that. But now we have columns, which are called fields in a database, but they're very similar to attribute columns inside of a GIS package. A little different from a spreadsheet because everything that's in a column, it has to be the same data type, the same length, etc. So more like an attribute table in a GIS, and there's a very close relationship there between the attribute table in a GIS application and a table in a database. Now this one has an ID. I highly recommend every table that you create to have an integer ID. These can be serial, which means the database, every time I add a new entry, like if I put one here for cheatgrass, and then I refresh my table, it'll automatically assign a new number. This is the PK, or the primary key. That means it will also be very fast to access using these numbers. Strings, and especially searching for strings in databases, is the slowest thing you can do. And PKs, serial PKs are the fastest. So recommend you have one of these in each table, and what this will do is uniquely identify every single row and allow you to get to it quickly. Then the different fields can be of different types. All of the major databases now support integer, some type of floating point, often called a double, strings of different types. Dates are inherently supported by databases, usually very well, better than just about any other application. And also geometric types you can now have in most databases. PostgreSQL does support geospatial data types, geometries for vector data, point, line, and polygon. It does that inherently, and it also has another addition called PostGIS, which adds spatial references and projecting into the database. Pretty cool stuff. Now you can see I've got a series of tables here. This is fairly common, but if you take a look at something like organism data, this is data for an organism, you're going to see that it has a taxon ID. That establishes the relationship between my taxon table and this table. This is data for an organism. Well, it's for that species. Again, this table has an ID. Now you may notice this table doesn't have a lot of stuff in it. It just has a taxon ID, a survey ID, and a dataset ID. Well, that's kind of boring, right? But it's actually pretty cool because what's happened is there's a dataset that this data came from, a survey which represents the time and the location of when the data was taken, and then it says it's for this species. Okay? Well, the rest of the data is actually in other tables. So if we go to organism measurements, you'll see that there is, again, an ID, and there's an organism data ID. So this column links the measurements that were made for that species, okay, back to the organism data. The organism data links it to a survey. Survey actually links it to a location, okay, and the data set links it to the data set that we got it from, because this database integrates together multiple data sets. Anyway, that's the relational part. I'm not going to focus too much on it because it gets complicated, and you want to start with just basic tables like I've done here. I'm going to go ahead and delete my cheatgrass entry, and we're just going to start off with one entry. And this is an old database, so I can play around in it and not worry about it breaking anything. When we talk to this from Python, we want to be able to select or query out data from the database. We also want to be able to add data and delete data, just as I did, and edit data or update data. Those are the four basic database functions that I use on a regular basis. I'm not officially a database manager, even though I use databases heavily and I use them a lot. Database managers or database administrators spend most of their career setting up databases, and they also work with all of these other things that are in here, like groups and login roles, setting up sequences and functions and other things, and they can create whole applications just inside the database. What I do largely is set up a database like this. I do a little bit of editing inside of these windows, and especially correcting problems when I'm first working with a database. And then I switch over pretty quickly to Python or another programming language, and I talk to the database through Python. Now, the reason to use a database over other things is because you have this type of relational structure where you've got organism data linked to a taxon and linked to measurements, especially when you have one organism data or one sampling of a species at a point in time and a location, and then you have multiple measurements. Like for fish, you might have fork length, weight, sex, any number of different measurements that are associated with one sampling of a fish or group of fish, and you might have that for one species, but you might do multiple species during the same survey, and of course you might have multiple surveys at the same location. So that's that relationship nature where you have one location related to multiple surveys. We can't do that efficiently inside of spreadsheets. We need a relational database for that. And then again, we have multiple organism data for one survey and multiple measurements for one organism data. So that's that relationship we call one-to-many relationship that you really need a relational database for to manage that efficiently. Okay, so how to jump into Python and do this. Again, I tend to set up my databases using the GUI that's provided by the database. Oh, and I should mention that you can do queries in here, and I do this periodically, again, especially when I'm testing out and starting up the database. Select star from taxon will select all of the fields from the taxons table. But let's go to Python, plenty of time in there. Okay, so here we've got the import that I need to use for Postgres to be able to talk to the database. It's this PSYCOPG. Don't know what that means other than Postgres, but that's the library you need to install to talk to Postgres directly from Python. If you're going to talk to SQL Server, you have to go through ODBC. You have to install an ODBC binding for Python. You have to, ODBC is the painful part of using SQL Server. Otherwise, SQL Server, I use it regularly. I kind of like their GUI a little better. MySQL is another one that's very popular, and it's also free. It's not as high performance as Postgres, but it's a little bit easier to use and get up and running on. Anyway, to talk to our database, we do a PostgreSQL or whatever that's called connection, and we pass in a database name, a username, and a password. So this is the login, and you need this for any enterprise level relational database. Some type of name, user, and password. Then we get a cursor. You may have seen this before talking to Arc. It's very similar to the way you talk to attribute tables through ArcPy, where you get a cursor, and that's going to be a way of searching through the features within the table in the database, or the rows within a table and database. Then you do a select. Now let's go ahead. I got a kind of complicated select string here, so let's start off with something really simple. And we're just going to go ahead and select the common name and scientific name from taxons, and then we're going to execute that SQL string using this cursor, and then we're going to fetch all the records, and then we're going to loop through the rows, because what's going to come back from fetch all is going to be a list of the rows that match our select. And then within each row, there's going to be a series of cells or the values for fields. I should go ahead and put a breakpoint. Okay, so we go ahead and run that, and you can see that it went into our database, and it got the common name Chinook, and then the scientific name, however you pronounce that. Okay, so that's it. Now we can do other more complex things. So I'm just going to go ahead and add my cheatgrass row back in here. Oops. Okay, database. There we go. Let's just go ahead and add a couple of things in here. And I'm going to go ahead and add cheatgrass. And I'm also going to add fall Chinook, because I want to show you a couple things. And I'm going to do Chinook. Well, let's do spring Chinook with small characters, which I really shouldn't do. You want to standardize everything. Okay, but let's just throw those in there. And now we can stop and rerun. And whoops. What? Where common name equals, single quote, Chinook. Okay, so I'm going to go ahead and run that. Equals, and notice you'll get errors back on the execute when there's a problem. May not be the best error messages, but it'll tell you which line it's on. If you really get stuck with your queries, what I do is I print them out, and then I jump over and go to the query editor inside of my database software. Okay, so you can see that only got one result, right? We had several, but it only got one. Well, that's because databases by default do a direct match to our table. Oops, got some extra tables floating around here. Okay, so in other words, it's not going to match these guys because this one is cheatgrass, shouldn't match that one. This one isn't just the word Chinook, it's got fall in there, and this one is small characters. So if we want to match a portion of it, what we need to do is use like. So like will match part of it, and then the percent and percent are wildcards. So if we do that, now I'm going to go ahead and match Chinook and fall Chinook. Now we're still not picking up the small character, and if I go, oh, well, I can just make that small, well, suddenly then I'm picking up the small one, but I'm not picking up the capital. So standard way to deal with that in Postgres is to just convert everything to lower. So there's a whole series of functions inside of SQL that you can use. This one will take the contents of common name, that field, convert it to lowercase, and then do the comparison with the string you specify. That allows us to go into the database and pull out all of the different versions of Chinook. Now again, you should probably standardize your database, but it doesn't always happen, and sometimes you want to search for a word independent of whether it's at the start of a sentence or in the middle. So this is really common search string that I use to find text inside of a string. Okay, so next we might want to add a new species, especially if you've got 10,000 of them in a spreadsheet. So this is an insert string. So it's going to insert into taxon. That's the SQL part. Then the table name. Then in parentheses, each of the fields that you want to insert data into. Now you don't have to do the ID because it's automatically set. And then notice here we've got values and then parentheses with a single quote around done salamander. Oops. Thank you. Okay. And I'm going to come back to that double single quote. Then there's a comma. Here's our second part, the scientific name, and then returning star. In fact, let's go ahead and do this. So, well, I'll explain now. So done salamander has a single quote in it, right? Done's would be a single quote. However, if we put a single quote there, it's going to terminate this single quote. So to get a single quote into a database, you do two single quotes, not a double quote. That's actually two characters there. So there's two single quotes. That's how we get around using a single quote inside of a database. Okay, so we execute that. We fetch all. Oh, I forgot to mention, at the end is this returning star thing. There isn't a standard way in SQL, and in fact, there's little differences between each of the versions of SQL for the different relational database. There is no standard for how to return the ID of a row that was just inserted. So in Postgres, it's this returning star thing. And then that comes back from fetch. And because that gives us a list of rows where there's then cells inside the row, we can get the first cell, contents of the first cell in the first row by doing 0 and then 0. And that gives us back our ID. And now we've got an ID of 17. We look over here. There's no 17. Well, the reason for that is this is a enterprise level database. So multiple people can be talking to the database at the same time. So it's actually created a temporary place to put this. And then we can do a commit. And now we do a commit. That change is committed to the database. Okay, and that's set up for what's called semaphoring, where one person can talk to the database and then another person can be talking simultaneously, and those changes are managed between different people. Okay, something more to learn about in a database class. If I want to update something, if I want to come back and say, wait, the salamander has another name, I want to add that into my other names column, I can say update taxons set other names equal to this. Notice the contents of the field is in quotes. Where, here's our ID, and this is where ID comes in, and then format with the ID that came back from up here. So this will execute very quickly without doing a search because it just goes right to that row that we have the ID for, that's 17. Now again, I execute that and commit it, and then it will appear over here in our other names for the salamander. Now, delete is also easy. In fact, it's a little bit too easy. If we just say delete from, and notice all of the standard SQL terms are capitalized. Table names are small. That's fairly common. Where ID equals this. Okay, if we do that, that will go ahead as soon as we commit it, and that will delete that row. Ta-da! Now you have to be extremely careful with this because a mistake that I make on a regular basis, quite honestly, is this one where I just do delete from taxons without a where clause. If you don't know what that does, go ahead and do it once and then you'll never do it again because it will delete everything in that table without warning you or saying, should you really want to do this? Or want to blow the whole table away? Yeah, that would be bad. So we don't want to do that. You always want to have a where clause attached to delete, and be careful with delete because you can blow away all of the contents of a table in one line very quickly and easily with no warning or anything. Now, databases also have easy ways to do backup. Backup right here in Postgres. You can do a backup very quickly. You can restore them relatively easily. So that's a good way to make sure that if you do blow something away, you can always restore it and bring it back. All right. Postgres, again, is free and relatively easy to use. Database class would be a good thing, but feel free to download it and play with it. Just before you commit to having a database that you're going to be working on professionally, probably want to take a class or at least read some books about database administration. Have fun.